So today we're going to review logarithmic laws and how they are related to that new number that we sort of developed or found out in the previous unit when it comes to exponential function derivatives. So going back, log BAX, so log form, is another way to express a exponential form. In other words, we can express a log form in exponential form B, where B the base, X an exponent, and A we'll call it the argument. Now keep in mind we have restrictions to B. B must be a positive and B cannot be equal to 1. And if B is positive, then therefore X is an element of real numbers, meaning it can be whatever it wants, and therefore A is going to be positive. So going back to the log form, B and A, they are going to be positive values. So how is the log form connected to the E? So when the base is a specific number, in this case, if we let the B be 2.718 or E, it's actually the same thing as writing down natural log of A. So this is another form of a log, a specific form where the base is a E. So the first rule we're going to talk about is the sum. When you add logs that have the same base, you multiply the arguments, AC. If we translate this into a specific base, in this case E, we get this. And we're going to reformat this into the natural log form. So log EA is the same thing as ln A plus ln C, or natural log. The rules still apply. When you add things with the same bases, in this case is base E, you take the product of the arguments, ln AC. Same thing for the log. When you subtract logs with same bases, you divide the arguments. So we do the same thing, log EA minus log EC is the same thing as ln A minus ln C, in which case you're going to divide the arguments. Now the last one here is the power law, or the power rule, where you can take the exponent of the argument and bring it to the outside of the logs. This should have been proven in the previous school year math course. So when it comes to base E, we do this exact same thing, a to the n, but we're going to change this log E into natural log, rewrite this out, and the same rule applies. The exponent of the argument can be reformatted to be the coefficient of the natural log expression. So here we're going to evaluate logs. To figure out what this number is, there's a couple of ways, but we can actually transfer this into exponential form. You have B as the base, the question mark as the exponent equals to the argument 1. And B to the power of what will give you 1? In this case, the question mark or the exponent will be 0. Anything to the power of 0 is 1. Same thing for in this case, the question mark, B to the power of what will give you the argument, which is B. And we know the exponent for this section is going to be 1, so the question mark is also going to be 1. So there's a pattern going on. If we do this, B to the power of what is going to be B to the power of n. We know that this exponent is going to also be the same as exponent of your argument, n. So now we're going to transfer, meaning we're going to have a specific value for B. In this case, I want B to be the natural number. In this case, log E1 would also give you 0, but we're going to reformat this in terms of log E. We can rewrite it as ln 1. This one, same thing, log base EE is equals to, in this case, it's going to be equals to 1. However, we can rewrite this in the ln form. In this case, this piece becomes ln E. And the last one here, if you have log E to the n, is pretty much the same thing as, we'll change this into the ln form, keeping the argument. You end up getting also n. So to evaluate this, some students have the special calculator where you have this specific button, but some students don't have the special button. They have just the log button, which is automatically default log base of 10. So to get the number here, the decimal number, we're going to have to use this specific law where you change the bases. So in this case, if you want to get log base 5/8, you're going to have to take log 8 divided by log 5, because all of our calculators should have a log of base 10. Now, how does that transfer into base of E? Well, if we want to change bases, we can actually change the base to a base of E. In other words, we can take log 5, 8. Change it into changing bases, log 8 base of e over log base of e5. In other words, we know that this here is ln a over ln 5, so we all should have the natural log button on a calculator. So when you take ln 8 divided by ln 5, you get exactly the same answer as this. So when it comes to solving exponential functions, there's a couple of ways right now. Over here, this is purely exponential form. You can go directly to change this into log form. So in this case, we have log, the base is a 2, the argument is 9 equals to x. So some students may have this in their calculator already. Another way is you could log both sides, meaning you take the log of both sides, log base 10 on both sides. In this case, you can take the x and use the power law. You have x log 2 is equals to log 9, and then this is a constant. You're just going to divide both sides and you get this. And if you notice, this and this are pretty much the same. This is a changing base rule. Now, let's just say you don't want to take the log of both sides. You want to take the natural log on both sides. You can. So you can take the ln natural log on both sides. Use the power, bring the x out. So it's the same thing as the one before, but now it's a specific log base, natural log. So also this is also the same thing. So these three values give you the same decimal place. So this is the last log rule we're going to go over. So when you have an exponential form, so this is like a composite type of, I don't want to call it function, but expression, where the bigger picture is exponential, but there's a log within that exponent part, the power part. If you notice, if the base and the base of the log and the base of exponential are the same, you end up getting m. Now over here, when the base and the base are the same, you don't exactly get m because there's a little coefficient on the outside. So we're going to have to use the power law and bring that n on the exponent of the m. So now this format looks very similar to this format. In our case, the bases are the same. We know that the argument is going to be the final result. So now we're going to link this into using the log base of e. So over here, I'm going to change all the b's into e's, 2.718, and we end up getting this. And we know that the log base of e form can be rewritten as e to the ln of m, and because this and this are pretty much the same, just change the base to an e, the result is going to be also m. Now, if we do the same thing for this rule here, changing all the e's, the b's to the e's, and there's a little n outside, we use the power rule again, log e m to the power of n. In this case, we can change all the log e's into lns, and we end up with m to the n. The result should also be. The reason why we're going over this specific rule is we were going to use this specific log law using base e to prove the derivative of b to the x, another proof for the derivative x without using first principles. So now would be a good time to actually go to Google Docs on Google Class, and I posted some questions for you to try in terms of how it's related to natural logs and all those log rules before we actually do the proof for the derivative of an exponential function.